Hello there, Mr. Sutton here, bringing you the BC Calculus 8-4 Extra Practice Number 5 solutions on vector free response practice. For this calculator-based free response problem, we have a particle moving in the xy plane on the time interval from negative to positive pi, given parametrically by x of t equals sine of 3t and y of t equals 2t. Well, that doesn't look so bad. First task on this is to sketch the path of the particle in the xy plane provided down here, and also indicate the motion of the path. So we're going to have to draw some arrows to let people know which way this thing is going. All right, well, in order to do this, we're just going to graph this in parametric mode on the calculator. So here we go. The first step we need to take is to go into mode, and down here where you see the func, you have a choice. These are different graphing modes. We want pair mode for parametric, so arrow down to there, arrow over to pair, and we have to press enter to get to that. And then if you go into y equals from here, you'll see that you have x1 and y1 instead of just y1. So now we can graph things parametrically. So we had an x of t here that equals sine of 3t. So we do sine of 3, and to get a t, you just have to press the x button, and it now is a t button. And we also needed the y version, which is going to be 2t. So let's put that in there under y1 of t. So 2t, there we go. And we probably want to do a window similar to what they have here. So let me go to window. Now for the t values, they said they wanted us to graph between negative and positive pi. So let me do negative pi right here. And it looks like I already had positive pi for tmax. Go me. For the xmin, we're going from negative 2 to the xmax of positive 2. So we might as well, again, use the same window they're using. I'm not sure how much of this zoom fit will actually give us. And then for the y min, well, let's see here. It looks like we're going down to negative 7 and up to positive 7. So we got negative 7 for y min, positive 7 for y max. And let's just graph this and see what happens. Okay, so we're going up like this. It looks like we started at the bottom and we're moving up. So something like this. In terms of arrows to show which direction we're going, we'll just show our arrows starting at the bottom and sending us in an upward direction here. There we go. More arrows, lovely arrows. One more for good measure. And there it is. For this part of the problem, they want us to find the range of x of t and y of t. So basically they're asking what kind of numbers can we get out of these two parametric functions. For x of t, since this is based off of a sine function, it's going to all come down to the amplitude. This is going to oscillate between negative and positive 1 because it's just one sine of 3t. So that means that because we have that amplitude of 1, we have a range of negative to positive 1 for x of t. Now for y of t, this one's linear. So that means that its range, it's all going to depend on the highest and the lowest inputs to this function, because it's just going to keep going depending on what kind of inputs you have. So the smallest input, or at least the most negative, was negative pi. Biggest input was pi. So this is going to range between 2 times negative pi, because we're doing 2 times the input, and 2 times positive pi. So then the range of outputs for the y of t function is going to be between negative and positive 2 pi. And on both of these, notice that the endpoints here are included. This is negative 1 less than or equals to 1, and same thing down here. For this part, we want the smallest positive value of t, for which the x-coordinate is at a local max, and they want the speed of the particle at that time. Well, I need to figure out then at what time x prime is changing from positive to negative. X prime, if I use the chain rule, is going to be 3 cosine of 3t. So let me graph that out. Now to graph that out on my calculator, I need to be in func mode. So I go to mode, and I actually changed back to func mode off camera here. So let me go to my y equals then. That's where I've entered my 3 cosine of 3t. And now notice it's back to being an x now that I'm in function mode. And for the window on this one, I'm going to be going between negative and positive pi for the x values. And then if we do a zoom 0, zoom fit, here's what x of t looks like. So the outputs on these are x values, the inputs are t values at this point, and it looks like we're changing from positive to negative at about this spot right here. Let me do second trace, option 2, and let me calculate that intersection. So move my spider a little bit to the left, press enter, a little bit to the right, press enter again, and then enter one more time to get the value 0.5236 if we round it out to 4 places. So here was that graph, and I'm going to call this value p. So I'm going to say x prime changes positive to negative at p, which is again approximately 0.5236, and I'm actually going to store that on my calculator because I'm going to need it for later. So let me go out of my graphing mode into the stow button, and let me store that as alpha p, or whatever letter you want. And there we go. Notice this is the number that we just stored. And let me just complete this thought here. So because x prime changes positive to negative at this value, therefore x has a local max at time equals p. So we found the smallest positive value for t then, where this is happening. At this point now we also have to get the speed of the particle. So for that you need both x prime and y prime. Y prime in this case, if you just look at the y function, that's just going to be 2, so that one wasn't so bad. And now for the speed, I'm going to need the square root of x prime of p squared plus y prime of p squared. And since I've already defined what p is and x prime and y prime, I can actually do all of this now on my calculator. So just to finish this off on the calculator, we have the square root. And now I need to do y prime of p squared. So I stored y prime as y1, or I should say x prime of p squared is my first one. I stored x prime as y1, so alpha trace y1. And then let me plug in alpha p, close the parentheses, square that. Plus, now I need to do y prime of p squared. Now the nice thing about y prime is that it's a constant function of 2. So I don't have to really plug in p because I know it's just going to give me 2 back. So let me do plus 2, but don't forget to actually square that. I guess you could have written 4 if you were feeling adventurous. And now let's press enter to get that square root. And apparently that whole thing is coming out to 2. All right, well, we'll take their word for it. For this last part of the problem, they want to know if the distance traveled between times negative pi and positive pi is greater than 5 pi. I think the easiest way to answer this question, since we have a calculator, is just to find that distance and compare it numerically to the value of 5 pi. So recall from part C, we have x prime and y prime given by these formulas here. That'll be helpful on this one. Now to find the distance traveled here, we need to do the integral from negative to positive pi of basically the speed of the particle. So we have the square root of x prime squared plus y prime squared, and we'll have a dt there. So this is how I wrote everything out just to justify my work. Now since I've already defined x prime and y prime, I can just write those in there without showing anything else. Let me do all this on the calculator now. So here's what all of this looks like on the calculator. Math 9 to get my integral from negative to positive pi. And then let's see here, we have a square root. I stored x prime as y1, so I can do alpha trace y1 and square that. And y prime is just 2, so 2 squared. Instead of t, I'll put an x, but I've been using x consistently everywhere else. So as long as you're consistent about your dummy variable usage, you're good to go. Press enter, and that comes out to total distance of, come on, it's because we were going back and forth with this cosine function. I didn't think it'd take this long. Oh, there we go. We got 17.973. Okay, that doesn't answer the question, though. They wanted to know if the distance traveled was greater than 5 pi. Well, what is 5 pi? If I go back to the calculator, let me just type in 5 pi. That comes out to 15.708 approximately. Because this number is bigger than this number, we can say that our total distance is in fact greater than 5 pi. So now the question is answered. For this calculator-based free response problem, we have an object moving along a curve in the xy plane at position x of t comma y of t. They didn't tell us what those were algebraically, but they did give us x prime and y prime basically here. And they also told us at time 2 the object was at the point 6 comma negative 3. First task on this is to find the acceleration vector and the speed at time 2. So for both of those, we're going to have to use x prime and y prime. So let me take a moment to actually plug those in the calculator. So I'm here in my y equals. In y1, that's where I'm going to store the dx over dt, x prime. And in y2, this is going to be y prime here. I used fancy fraction mode to make that happen. And I used second sign to get sine inverse. Might have been a while since you used that one. So to get the acceleration vector, acceleration is going to be x double prime of whatever you're plugging in, so 2 in this case, comma y double prime of 2. So this is the general setup that we need to do. Now the good news is that I already have x prime and y prime defined up here. So I'm allowed to just take the derivative of a function, which is basically what we're doing with x double prime and y double prime. I'm allowed to take the derivative at a single spot without actually having to find the derivative algebraically. So I don't actually have to figure out the derivative of arcsine of all this stuff. I can just take the derivative of this on the calculator at 2, and since I've already got the original function here, I'm good to go in terms of showing my work. So let me go ahead and do that on the calculator. So going back in there, let me quit out of my y equals, and I'm going to do math 8 to get my derivative. I'm going to do dx, and if I need the derivative of x prime, I'm going to do alpha trace y1. This will now give me x double prime, and then I'm doing that at the x value 2 to get the value about 0.396. Now we have to do the same thing to get y double prime. Let me go back and yank my input from before. So the only thing I really need to change from my input is I want to take the derivative of y2 because that's where I stored y prime in the y2 function. Still doing that at the input value of 2. Press enter, and that's negative 0.741. So that's our acceleration vector at time 2. To get the speed at time 2, I need to do the square root of x prime of 2 squared plus y prime of 2 squared. This right here. And that's another one that I can do on the calculator. So to do that on the calculator, let me do square root. And then I got to do y prime of 2 squared. So alpha trace y1, and I should have said x prime of 2 squared. So we have y1 with 2 plugged in, and then close that parentheses and square it. And then to get y prime of 2 squared, we'll do alpha trace y2, plug in 2, square that, press enter, and that's 1.208. And since they didn't give us units, we don't give them units back. This one's done. For this part, we're told that the curve has a vertical tangent line at one point. We want to know at what time the object is at that point. So we're going to have a vertical tangent line if x prime, which is the left-right motion, is 0. We don't want any left-right motion. But at the same time, at that spot, y prime has to be something that's not 0. We need some kind of up-down motion to have a vertical tangent line. Otherwise, if they're both 0, if x and y prime are both 0, your particle is just standing still. So we're going to start by taking x prime and figuring out where that takes on a value of 0, and we're going to do that on the grapher. So to do this, I'm going back into my y equals now, and I need to basically figure out where this y1 curve hits the x-axis. So I'm going to deselect y2 because that was y prime. I don't need that. I'm just graphing y1, x prime. I'm not really sure what window I should use, so let me just do, it's probably close to the origin, so let me do zoom 4. I can always change the window if I need to. And we do indeed cross the x-axis right around there, so that was a good lucky guess there. Let me do second trace 0, option 2, and then let me click once to the left, once to the right, and once again. Our intersection happens at 0.6931 if I round that off. So there's my graph, and I'm going to call this point, I'm going to call this value A, so 0.6931. So now I can refer to that pretty easily just by saying A. In fact, I'm going to go on my graphing calculator, and I'm also going to store that value. So let me quit out of there and store that as alpha A. So now I can pull that back whenever I need to. So this is a spot where there's no left-right movement at this time here. But we also have to establish that the y prime of A is not 0. So let me plug A into y prime. And to do that, I'm going to go on to the graphing calculator again. So now remember I stored y prime of t in y2. So let me do alpha trace y2. And then I can just plug in A. So plug in alpha A. Close the parentheses if you want. And that comes out to, okay, 2.0, I guess, 80 if we round that off. Now the important piece of this, did it come out to 99? Yeah, I guess I can go to 4 decimals. Doesn't really matter. The important piece of this is that it's not 0. That establishes, since we have 0 for x prime at that spot and not 0 for y prime at that t value, that establishes that we do have indeed a vertical tangent line at time equals A. On this part, they're letting m of t represent the slope of the line tangent to the curve at x of t comma y of t. So basically this is dy over dx. And they want an expression for that in terms of t, and also they want the limit of that function. Okay, well, in order to find that, when you're doing dy over dx for a parametric function, it's basically y prime of t over x prime of t. So I'm going to write that. And since I've actually already got y prime and x prime defined, there's x prime, there's y prime. That's just another way of representing them. It's understood that these are x prime and y prime of t. I can write this, and I've actually satisfied that part of the problem. I have defined m of t in terms of t. Now, to use this to evaluate limit as time approaches infinity, I'm going to write a little bit more in there. So this is going to be the limit of, and now I've got a big fraction. In the numerator, well, I normally had y prime of t, but that's actually a big fraction. So the only thing that stays in the numerator from this fraction is going to be this 4t that was already in the numerator. Now downstairs, this 1 plus t cubed is moving. And we also have this x prime that was already down there. Sine inverse of 1 minus 2. I'm going to call this 2 over e to the t, just so it's a little easier to take the limit. Now, as time approaches infinity, I can ignore the slower growing value of 1 in here. So I don't need that 1 plus the t cubed. I can just write t cubed. And over here, I can actually zero out this 2 over e to the t because that's a bottom-heavy fraction. So that goes to 0. So I just have t cubed times sine inverse of 1. And really what it comes down to here is this is a bottom-heavy function overall if t is growing to infinity because t cubed is way faster than t. So this whole thing is just going to go to 0 when all is said and done. For the last piece of this problem, they're telling us the graph of the curve has a horizontal asymptote at y equals c. Write but don't evaluate an expression with an improper integral that represents this c value. So if I'm talking about horizontal asymptotes, I'm essentially talking about the limit as time approaches infinity of y of t, because that's the function that's in charge of my my y coordinates. So to get that, I'm going to have to do what I would do to find the value of any value of y, really, which is to start with the initial y value, which was -3, and add the integral from, let's see, that was at time 2. So the integral from 2 to whatever time of y prime. Now, what's the whatever time that I want to go to? In this case, I want to go to time infinity. So I'm going to do -3 plus the integral from 2 to infinity of y prime of t dt. This is an improper integral. We have an infinity in the limits of integration. So this is what's basically going to tell me if I evaluate this. It's going to tell me my y value that I'm approaching at time infinity. For this calculator-based free response, We have a particle moving along a curve in the xy plane given by x of t comma y of t. They didn't tell us what those actually were, but they did give us the derivatives of both of them right here. So basically this is x prime and this is y prime here. That's how I'm going to refer to them for large parts of this problem. And we're also told at time 0, the particle is at the point 4 comma 1. So given that background, we now want to, for our first task, find the speed of the particle and its acceleration vector at time 0. All right, so to find speed, I'm going to need the square root of x prime of the input, so x prime of 0 squared, plus y prime of 0 squared. So basically this setup right here. I've already got x prime and y prime defined up here, so I just need to put those in my calculator and really plug all of this into my calculator. To make the rest of this problem easier, both this part and later parts, I'm going to enter, again, both of these in my y equals. So dx over dt, x prime, I've got in my y1. And in the y2 here, this is dy over dt, y prime. And notice that I'm using x's instead of t's because that's what my calculator likes for the input if you're just in this regular function mode that I always use. So quitting out of there now, I'm going to do basically this square root business on the calculator. So we have square root of, and now to get x prime of 0 squared, I will do alpha trace y1 because that's where my x prime is. Open the parentheses, put in a 0, close the parentheses, and to square that, you just square right outside there. And now I'm going to do the same thing for y prime of 0, but I'm going to do alpha trace y2, and now plug in 0, square that, press enter, and that's 7.616. And they didn't give us any units in this problem, so we're not giving them any units back. Don't forget, though, you also needed to find the acceleration vector at time 0. So for that, we need to find x double prime of 0 comma y double prime of 0. We don't know what x prime or x double prime and y double prime are. We could certainly find them by taking the derivatives of these two functions up here. But the good news is we actually don't need to know what the derivatives are to take the derivative at a single point on our calculator. All you need is the thing that you're taking the derivative of, which we have up here, and you just need to plug that in with your point in the calculator. So this is all we have to show for work because we already have x prime and y prime, and we're just doing this at a single input value. Let me do this on the calculator now. So for my x double prime of 0, I'm going to do math 8. That gives me derivative. I'm going to do dx, and I want to take the derivative of x prime, so that's going to be alpha trace y1 that I'm putting in there. And I want to do this at 0 for time, so I'll plug in 0 into that little x box down there, press enter, and well, that comes out to 0. Okay. Now I'm going to do the same thing for y double prime of 0. So I'm going to yank my input from before, and the only thing I'm really going to change, I want to now take the derivative of alpha trace y2 because that's where I stored y prime. So taking that derivative will give me y double prime of 0. And that comes out to, well, if I round it off to 3 decimals, that's essentially -3. For this part, they want an equation of the line tangent to our path of the particle at time 0. So for a tangent line, I need an x value, a y value, which I actually already have because they said at time 0, this is the point that we're at. And I also need the slope. I need dy over dx specifically. So to get dy over dx parametrically, at 0, I need to do y prime of 0 over x prime of 0. That's how it works with these parametrics. The good news is I've already got y prime and x prime defined on the calculator. So let me just go ahead and plug that in. So here's the setup that I've done on my calculator. I put y prime as y2, so I did alpha trace y2 in the top of this fraction, and I've got 0 down there. And then I did alpha trace y1 of 0 down here because that's what x prime is y1 in my calculator. Press enter. That comes out to 7/3. So in order to get that into the equation of a line, I'm going to have y minus the y value that they gave me, so y minus 1, equals my slope that I just found of 7/3 times the x minus the x value here, so x minus 4. And there's no need to simplify this. We're done. For part C, they want us to find the total distance traveled by this particle from time 0 to 3. So for this, I basically need to integrate the speed of the particle over this interval. So I have the integral from 0 to 3 of square root of x prime squared plus y prime squared. And we'll have a dt for the differential and all that. So I can just do all of this on the calculator now, since x prime and y prime are already defined up there. So here's what this looks like on my calculator. I did math 9 and then 0 to 3 for the integral. I've got square root of, and if I want x prime with nothing specific plugged into it, I just do alpha trace and pull up y1, and then I can square just that directly. Same kind of deal with y prime right there, which I stored in y2. Press enter. Wait a little bit. That comes out to 45.227. For the last part of this problem, they just want the x-coordinate of the position of our particle at time 3. So we're just going to use fundamental theorem. Basically going to have the initial x value, which was 4, plus the integral of x prime from, let's see here, we need to go from time 0 to time 3. So integral from 0 to 3 of x prime. There we go. And now just plug it in the calculator. So here's what that looks like on the calculator. I stored x prime as y1, so we're just integrating that from 0 to 3. Don't forget that 4 in the beginning, and press enter. That all comes out to 17.931.